Good afternoon, everybody. My name is Changho Choi. I'm a member of Memory Solutions Lab in Samsung Semiconductor in USA. This work is collaboration with other members in our group, Jingfei and Rajinikanth and BJ. Here's the agenda that I will discuss today. The first I will discuss SSD NAND flash characteristics and some concerns that industry has. After that, I will discuss multistream that address that concerns that industry has. But as you know, multistream has a good bring a lot of benefit, but it has some caveat. So as you imagine, we address that kind of caveat with automatic stream detection algorithm, that is AutoStream. We developed two algorithms. So first one is multi-queue and second is SFR. We'll discuss details of this algorithm. After that, we'll review the performance benefit for each algorithm, and then I'll conclude my talk with some summary. Let's start with SSD NAND flash characteristics. As you know, SSD is composed of NAND flash cells. NAND flash has different characteristics compared to HDD. As you know, in the NAND flash, when you read or write data, you need to do different unit compared to HDD. HDD, we are in general using sectors of 512 bytes. But in NAND flash, read and program is occurs in the page unit. That is generally 8 kilobyte or 16 kilobyte. But when you delete data, you need to delete multiple pages at the same time together in the unit of a block. In general, one block is 128 pages. And another characteristics is that you need to erase a NAND flash before you program. Because of these characteristics, you cannot do in-place update. Based on because of these two characteristics, SSD must run garbage collection. So this is one of the kind of big overhead of an SSD. In general, if the garbage collection overhead is high, the write amplification is high also. Higher write amplification can shorten SSD lifetime. So that is things we'll address. And finally, NAND flash has a limited number of program erase cycle. As we move from single level cell to triple level cell, as you see in this graph, NAND flash endurance went down almost 100. So to maximize SSD lifetime, we need to minimize write amplification and reduce garbage collection overhead. As we discussed in the previous slide, higher WAP will reduce SSD lifetime dramatically. So we developed a technology called Multistream to minimize write amplification. The basic idea of Multistream is that we store similar lifetime data into the same erase block. Similar lifetime data means that the data will be invalidated together through the delete or update operation. So in the multistream, the host tags data with the similar lifetime data. We call that tag as a stream ID. Okay? This stream ID tag the data delivered to SSD through the multistream interface. Multistream interface you could consider as a protocol between host and SSD. When data arrives in SSD will place the data according to that tag. In this example, we assume that there is 3 different lifetime data, like a hot data, warm data, and cold data. The application tagged the data based on this temperature, and then they deliver the data to SSD. As you see in the SSD internals, the different lifetime data is stored in the different erase block. In this way, we could minimize write application during garbage collection, and we could increase SSD lifetime. Multistream provide a great benefit to reduce write amplification and garbage collection overhead. But one caveat of multistream is that it requires application and system changes. It is really challenging, especially for multi-application and multi-tenant environment, such as virtualization, like a VM and Docker environment. In this environment, if one application uses one stream ID, that stream ID should not be used the other application in that system. Otherwise, the multi-stream benefit will be minimized. To address this issue, we developed an automatic stream management algorithm called AutoStream. AutoStream independently detects data lifetime. We predict the data lifetime and assign stream ID independently without any application help. We implemented this one in the device driver, inside the device driver. AutoStream cluster data into streams according to their data update frequency or sequentiality. We'll discuss algorithm details in the next slide. In this way, we could minimize stream management overhead in application and systems. As you see here, so AutoStream, we get rid of application and kernel modification requirement. Here is a high-level description of AutoStream framework. As you see here, read I/O just bypass AutoStream. So the read I/O would not get any kind of a significant overhead. Also, even for write I/O, when write request arrives in the device driver, it will just get the stream ID from AutoStream algorithm modules. That stream ID, getting stream ID is one table lookup. So the overhead will be negligible. Here's the architecture that we implemented in the Linux device driver. As you see, here's the AutoStream module. This is independent from device driver. This module will be interact with the device driver. When write operation arrives in the device driver will send the starting LVA of that write and request the size. And AutoStream controller put the starting LVA to submission queue. And then we'll do a table lookup to get a stream ID. And return stream ID to the device driver. And device driver will embed that stream ID to the write command and send it to SSD. Based on the stream ID, SSD will isolate the data from another lifetime data. In a background thread, the multi-queue and SFR algorithm, they will process one entry from submission queue. Okay, we'll discuss the details from next slide. Okay, let's look into first algorithm. That is a multi-queue algorithm. So multi-queue algorithms divide the whole SSD capacity into same chunk size. Let us assume that the chunk size is 1 megabyte and SSD capacity 480 gigabyte. In that case, we will maintain 480,000 chunks. And then we track statistics for each chunk especially for write command. Multi-queue tracks access time, access count, and expiration time, like a future expiry time. That is kind of a estimation of the future access for that chunk. In addition to that, multi-queue maintain a hardest chunk's lifetime. The hardest chunk's lifetime will be calculated with the difference between the last two consecutive access for that chunk. This hardest chunk's lifetime is used for set up other chunks' expiry time. This expiry time will be used for promotion and demotion, meaning that we will dynamically adjust the stream ID. We'll discuss that one in the next slide. Let's see the one example. Access time 11, let us assume that the chunk C is accessed. At this time, C is the hottest chunk because based on access count. And the hottest chunk is C, and C's lifetime is calculated with some difference, this one and the last access, that is 6. Let us assume that at access time 12, chunk D is accessed. At that time, chunk D's expiration time will be calculated. There is a current time plus a hottest chunk's lifetime. Okay. Multi-queue maintains some number of queues. In this case, it maintains 8 queues. Each queue represents one stream. So in this case, we have 8 streams. When multi-queue process one entry from submission queue, in this case, think about chunk F. As you see here, F is the first entry that occurs in this situation. In that case, the multi-queue push F in the first queue, that is the coldest queue. And when we push the entry to the queue, we just push it into the tail. Let us assume that as in the multi-queue process another chunk A. When A is accessed, they increase access count, and suppose the access count is chunk A's access count is bigger than Q1's threshold value. In that case, we promote this chunk from current queue to the next queue. In this case, chunk A is promoted from Q1 to Q2. After multi-queue completed promotion, they check each entry in the queue and then check if that entry is expiry time has passed or not. Let us assume that chunk is expiry time has passed. In that case, we demote that chunk to the lower queue. In this way, we could dynamically adjust stream ID based on their frequency and recency. Multi-queue provide some good characteristics to adjust the stream ID based on frequency and recency, but it uses a little bit more resources to optimize resource requirement. And also, we sometimes think some sequentiality is important. For example, think about one big file. When you write a big file, that could be sequential write. So in that case, if you put the same file in the same erase block, that would be better, because when you delete or update the file, they would be invalidated together. So we developed a new algorithm called SFR. SFR leverages sequentiality, frequency, and recency. The sequentiality part, okay, when AutoStream controller gets a starting LVA and request size, it checks if that write is sequential to the previous write. If that is a sequential write, then it just return. Oops. it just returns the previous stream ID. Otherwise, it will read stream ID from the stream table and return to the device driver. And device driver it'll embed this stream ID and deliver to the device. Like a multi-queue, SFR also runs the background thread. During the background thread, in a background thread, it processes submission queue one entry at a time. When SFR processes one entry, it increases access count, and also it calculates the recency weight that count like what is the last time access from the current time. If this time difference is big, then we'll adjust the access count accordingly. And with the recency weight and access count, we calculated the new access count. Based on update access count, we assign new stream ID. In this way, we could adjust the stream ID based on frequency and recency. Here is a representative performance evaluation result. We ran the two MySQL instance and two Cassandra instances in one Docker environment. As you see here, both algorithm reduce WAF almost 40%, meaning that both algorithm could increase SSD lifetime almost 2x. In addition to WAF benefit, as you see here, performance, MySQL performance increased more than 100% with these two algorithms. Cassandra's performance benefit is not that high as MySQL, but still we could get a performance benefit for Cassandra also. Okay, here's a summary of my talk. The first thing is we developed a multistream to address SSD issues. But the multistream has some caveat that requires application and system changes. So we address those kind of issues with another automatic stream detection algorithm called AutoStream. So AutoStream doesn't require any application and system changes. Without application and system modification, we could improve SSD performance and SSD lifetime. We measured the AutoStream benefit under the different workloads for diverse applications on various system environments. We could get up to 60% WAF reduction, and we could get up to 237% performance improvement. Okay, the current work is mostly done in the host side. We also considering to optimize the resource utilization, resource requirement to push down this AutoStream algorithm inside SSD. If we implement AutoStream inside SSD, then it is totally transparent to the host and application. So in that way, we could provide a benefit for normal SSD. Okay, thank you for your attention.
Questions?
Hi, I understand how the rectification is reduced, but what I don't really understand is why the performance of benchmarks you run gains speed up.
Okay, in general, as you know, the performance gain mostly comes from garbage collection overhead reduction. Think about this: when you reduce garbage collection overhead, meaning that you expose more SSD resource to the outside, meaning that you could increase I/O bandwidth for SSD. In that way, you could get a better performance.
So it's only besides from clearing up more disk space and making the garbage collection more optimized.
Okay, so optimized garbage collection meaning that let's assume that normal garbage collection take like 10 seconds, for example. This is like a random number. Okay, but if you using multistream and AutoStream, we could reduce like 5 seconds or 1 second. In that case, they could extra time to process more data, right? Like let us say 10 seconds and 5 seconds. So in that case, you could process 5 seconds more data. In that case, from application point of view, you could send more data, right? In that way, you could get an application benefit.
Thank you.
You've shown, initially, you suggested, and obviously that's a little bit hard, that if the applications could coordinate and tell the driver what kind of stream to use, if we could do that, that might have been better. Do you have any idea of how far SFR and NQ are far from like the optimal, impossible perhaps change to do this?
Okay.
Like how good it is at predicting?
That's a good question. Actually, we have in the paper we compared some like a tentative workload like FIO and Cassandra, because as you know, for Docker system, it is very difficult to deliver application assigned stream ID to the device driver. Right. So we measured that benefit in the Cassandra one application case, and also we measured some kind of FIO. So FIO case, we could match application assigned one, and Cassandra one, our performance benefit sometimes is better than application assigned one. But you know, it depends on how efficiently you assign the stream ID in application. So we did some more performance measurement on Cassandra, but we thought that is a kind of best algorithm. But sometimes it is matched, sometimes this algorithm is so better, sometimes it's worse. There's some small variation.
I'm curious that it appears you're tracking access to these chunks that are so much larger than the size that's in fact being allocated to the OS by the OS, so that you know, it's I wonder what 256 times bigger or so. Do you think that, what type of effect do you think that has on, do you think that more fine-grained tracking would give you better information or not?
That's a good question also. Actually, in the paper, we did some comparison based on the chunk size. As at least for SFR and MQ size, multi-Q size, when we did change the various chunk size, we get a best performance at 2 megabyte chunk size, at least for our measurement. And SFR case, we could get a best performance with 1 megabyte chunk.
Which file system?
We use the XFS file system.
We have time for one.
Sure.
I would argue that while you can increase device lifetime, the translation to performance is not so obvious. The reason is that applications that are latency sensitive force you to operate well below 100% utilization because of queuing stochastic behavior, which means that the SSD has tens of percents of idle time. This idle time can be used to do the garbage collection in the background. So although it's true that you need to do more work, that work can be done in the background and does not when you're using the available time anyhow. So you have to be a little careful with that.
Okay, so I think there is a kind of a trade-off, because as you know, if you increase the over provisioning size, for example, you just use like a half capacity, for example. Some application like aerospike guys, they use the half capacity of SSD to get a better latency or something like that. So latency and performance is kind of a trade-off, but as you know, if you reduce the effective capacity, yes, you could get some kind of extra time. But as you know, if you saturate the disk I/O, then as you know, the storage would be a little bit different. Suppose that you saturate the disk I/O.
If you saturate disk I/O, then what you're saying is right.
Yes.
But then the applications need to wait queuing delays, because the server, the SSD is.
Yes, that's correct. But in this way, you could reduce garbage collection overhead. Application will get the benefits, right? In that case, we could talk about more. Yeah, latency one is interesting question also.
We're out of time, so other questions, please let's take offline to our speaker. And thank you again.
Thank you.